So we have a lot of things to talk about here. This is going to be about Apache Drill, which just recently had a 1.0 release. It's a big deal. It's an interesting project. I'm going to be talking about that. The original speaker was Michael Hausenblas. He says that he's very sorry he couldn't make it, but he can't make it. He had to be at a big product launch. So I want to talk about Drill. And Drill is a surprising project. It's SQL on Hadoop, that sort of thing. Actually, it's SQL on all kinds of things. And that's what Andrew Bruce said about it recently in GigaOM, that it really is not just SQL on Hadoop, but it's SQL on just about everything you could imagine. So we're going to talk about it. What is it? What makes it special? And a little bit on how this is done. Now, unfortunately, I have a lot of slides, so I'm going to have to go fast. The slides will be available, though, for reference, and you can go in. It may be difficult to read some of the displays and things like that, but you can go back in and take a look at it later. But you can also try these things very easily. MapR has a special, by registration, sort of button you can push. It will spin up a 5-node cluster that will last for 6 hours, and you can play with it. Drill will be pre-installed, data will be pre-installed, so you can just try it. You can also just download it practically during the talk here. It takes about 5 minutes to install. You untar it, and it just runs. Now, the first thing that Drill is it's SQL. You know, maybe not in your family, but in my family, of course. We had these things at home and in the kitchen and that sort of thing. So this is SQL like you've always expected and always known. It has the standard sort of syntax, no strange exceptions. It has all of the standard types, all of the decimal types, the var binary, the var char, the different forms of doubles, and so on. Subqueries, correlated subqueries, pruning, an enormous range of complex SQL constructs are there. It therefore supports standard BI tools, Tableau, anything that uses ODBC, Excel, all work with it, and all of the standard Hive UDFs and SERDES also work with it. Works with the Hive metadata catalog. So it's also Punk SQL because it does a lot of different things as well. Starts with the standard, but then extends it in some very, very interesting ways. Notably, it has more modern syntax available so that we can access very directly recursive objects. So if it's an array, you use square brackets to index into it. If it's objects, you do standard JavaScript-style dot notation to navigate into the objects that are stored in the data. And those objects are first class in Drill, so you really can do interesting things that way. You also have file systems as organizing principles. These were largely, SQL is so old. This sounds like a joke, but it's not. SQL is so old that it was invented effectively before modern file systems were invented. So the idea of wildcards and path names are after SQL. Therefore, SQL has nothing in it that really recognizes it. Drill extends that so that directories of tables can be viewed as a single table by itself. And you have elements of the columns that you get back which describe the path that Drill took to get to the data. We also have more interesting data types. We have one that's called any, which means any type could be there. We have maps, we have lists, and so on. The any type is the key to another capability Drill has, which is late typing, which is almost like dynamic typing. SQL itself, regulation ordinary SQL, is a strongly typed language and an early binding typed language. It has to have all of the types of everything declared in a schema before you can even parse SQL. Drill has extended that so you can parse with partial typing information. Ultimately, you may just say, they seem to claim that that's a table, therefore I assume it has records of type any inside it. Now, later I may find out more about the typing, and I may be able to compile and optimize to a more detailed level, and then the type will be resolved down to a primitive type, but that will be late binding of typing. And that gives some very, very flexible capabilities, like the ability to interrogate data where the column names are not even known until you read the data. So that's exciting. That then requires a number of other operators to make that true. I'm going to show you examples of that. So if you have sensor analytics, or if you have data that's changing its structure and its type over time, you don't have to use alter table to go in and fix that. You can just query the data as it is. So let's talk a little bit about how it does it. Drill is flexible, which of course leads to a certain agility and the ability to jump high buildings. It's flexible and it's simple. To install Drill, you need one process to run. It could be an interactive process with an embedded so-called drill bit. Or you could have a drill bit that runs as a long life process on your machine like a database server, even though it's not really a database. Or you can have clusters of them running. We've tested up to hundreds of them, and the design is designed carefully to avoid n-squared sort of non-scalabilities. It scales up quite linearly and produces very, very high performance. So very, very easy to build a system around Drill. You can do with a clustered system, with MapR, with ordinary Hadoop distributions, or without, on a single machine or on many machines. However you want to get to the data, however you want to execute it. It's very easy to do. Now, part of the flexibility is not just in deployment, but in the data typing itself. You can imagine that data has multiple axes. You can talk about how flexible the data is in terms of whether or not it has a schema that's predefined or not. At the schema end of the world is relational data, where you have to have a schema in order to even store the data at all. On the completely unschema end of the world, you have JSON or BSON or things like this, where the data itself is the schema. You can also have data which has complex data types, or data which has only simple data types in very regular fields. And what Drill does is it takes us from the inflexible, non-complex world of relational data, where the COD definitions of what relational data are take us directly to that definition, to the completely flexible end of the world. The data layer, the data model inside Drill is essentially JSON. The data representation is not, the data model is. It's that flexible. Now, obviously, it can handle schema-full data, but it also handles schema-less data, even in the same query, even in the same table at the same time. So Drill doesn't require schema, but it can use it. The query can be planned on files or tables with or without early information, and it can bind late in the planning process, and it can generate code that's efficient that way. The guiding principle here is that Drill will operate at very high speed with no metadata centrally stored and no metadata until we read the data, but it will also use that data as soon as it can get it, so it will operate even faster when you have more regular data. Let's walk through some examples. And these examples are taken largely from the Yelp standard data set, which is a dump of the Yelp database that's intended for use as research or educational purposes. We can't redistribute it, but we can show you examples from that. It's nice because it has a couple of properties that make it very difficult to work with from the standpoint of a standard database. For one thing, all the data is stored in JSON, in files. Well, that's incredibly inconvenient from a database point of view because there is no data model. It's not defined ahead of time. You have to kind of look at the data and understand it. And here's some of the data there. This is a business description of something that is on Las Vegas Boulevard in Las Vegas. It sells French steakhouse kind of food, whatever that could mean. It's good for dessert, late nights, and so on. That's an example of it. And you can find data in it like, here are the votes that a particular business has had. That's a different file in there. And you can understand it because the data is well labeled, and it's easy to see when the schema is integrated in there. You can go from nothing to getting real query results in about 2 minutes with Drill. So installing it is nothing but untarring a tarball. So running it is running a standard utility called SQL line, which connects via JDBC to an embedded drill bit. And from there, we can directly query data in the file system. This is literally all you have to do to get started with Drill. You can do more things if you want a large parallel instance, but if you just want to try it, this is how much it takes. And notice here, what we would normally call a table name says it's on the distributed file system in a workspace, a directory, a predefined directory called Yelp, and then there's this file called business.json. Now the structure of that has state and city. We're going to order it by the number of businesses, and we're going to count the number of businesses there. The standard sort of reporting query that you'd expect, except that these were from a JSON data file, not from a conventional relational table. We get a conventional looking relational result, even though we're not querying relational data. Here's another example. This is more complex. Notice that the references here have multiple dots in them. So we can say, well, let's come down here. We're going to query from this file, business.json called B, and we're going to say b.hours.friday, 2 levels of indirection, because that's nested data, is less than 2200, and the closing point is greater than 2200. We're finding out what's open right now, late night in Las Vegas. And we can also say, and there's a list that contains Mediterranean. A list is a data structure, but it's not a data structure that you normally query inside a SQL query. So there we get olives, and it's open right now, it has Mediterranean and restaurant. There's another one, which is the Marrakesh Moroccan restaurant. Both of them open at 10 o'clock at night in Las Vegas. We can do all of the sort of things like we can say the business idea is in the result of another query. We're going to group that by business ID having a sum of votes greater than a certain amount. There's this sort of correlated subqueries works just fine. All of the sort of SQL structures still apply. Here we get the ability to build a view. Now, views I'm going to talk about more in a little bit, but views are essentially a file that has a snippet of SQL in it. So they are not materialized views, they're virtual views, but they can be chained. One view can refer to another and another. The exciting thing about views is not the fact that you can chain them. I could have just written the query, but the fact that permissions can be delegated according to that chain. One person might have permission on a table. They could create a view which accesses the table, and they could open up the permissions on their view. Somebody else could have permissions to read the view, but not the table. Well, they could recreate a view that references the view. This allows us to do things like on-the-fly decryption. It lets us do things like line-by-line masking of data. If we have a column which says this data has been withdrawn from public view, we can do filtering that way. We could also build materialized views or new tables, this sort of thing. We can work with repeated values, that's arrays of things. And this begins to be pretty exciting. We can do things like flatten. So before the data has these lists of categories, and when we flatten it, these become rows, which let us do queries on contents of arrays as if they were already data that had been flattened. Another good use of this is if you want to compact many, many, many samples or many, many data points into a single row in a database to make insertion and retrieval very efficient, or even compact them into a binary representation, flatten then can turn that back into what looks like relational data. If you have a time series database, you might insert 1,000 samples and timestamps into the data, but then when you retrieve it, you've only retrieved one view, you use flatten, you get 1,000 samples. But the data is not changed, is not moved, is not transformed by flattened. It's merely how Drill thinks about the data. The data is still stored in a flat, primitive, column-based representation. And so this goes at very, very high speeds, much faster, sometimes 1,000 times faster than the underlying database would allow you to operate on it if you were operating on a row-by-row basis. So flatten is a new capability that's very exciting. It's essentially a lateral view. Now, we can do recursive things against flatten, treating that as a view or as a subquery. We can even do some interesting things. One of the I don't want to say beautiful, I don't want to say bad, I don't want to say perverse, but it's all of these things. One of the things that happens in NoSQL databases is people put data into the column names. So because you could have sparsely populated columns, you could do something like, if you have a web page, you could say the domains that web page refers to have the columns with the name of the web domain that they refer to. And then the anchor text could actually be the value in there. So the column name itself is from an open set, something we don't have predefined, and it contains useful information itself, the domain name. Here, we have an array. Here's a magnified view, and this is an object, and the keys are time ranges. So 13 to 2, 11 to 6, and so on. And then these are values associated with those ranges. This is a very peculiar thing where the column has a name which is the combination of two sorts of data elements. Doing a query against that, we can use something called kvgen. That converts this one object into a list of key value pairs, and then we can flatten that kvgen, and we can do a query. So here's the result of the kvgen. So before, this was the name of the column, and so now we have one object with a key and a value, and so now we can do queries against that one value, like here, flatten, kvgen, and we get rows with those things. And that means that we can then do queries, flatten that, and now check in, key is 23-0. So how many restaurants have had a check-in from 11 o'clock to midnight? A very, very flexible sort of query, but nothing like what you could do in a normal traditional SQL database, but something you have to do if you want to manipulate very, very flexible NoSQL data. These data are the things that they come to you as they come to you. It's not something you can change. It's not something that you can manipulate. I talked to one customer. They have something like 40 or 50 million retail items that might be for sale. They come from 120 different business units. And each of the business units changes their schema on average twice a year. That means almost every day the schema of the collective data changes. And the IT department is supposed to deal with it. How are they going to deal with it? They can't control it. They can't even document it. They have to query it, even so. Well, techniques like this would allow them to succeed. Drill would allow them to live in the very dynamic, out-of-control world that they have to live in. And traditional SQL systems, which assume that you have a curatorial role and control over the shape of your data, would necessarily fail. Drill also looks at this decentralization problem and tries to apply a decentralized but still secure security model. The idea is that you will have perimeter security, tools like Tableau, or you might have Sentry or something like that. Those are controlling which kinds of queries you can do. They're trying to say you can't select against this sort of thing. But they are inherently holy. They have holes in them because it's very difficult to parse and understand what queries are doing and whether or not it's dangerous things. But then Drill also has distributed security at the file system level. And the way that that works is based on these views and the ways that views allow you to delegate your read permission in controlled ways to file system assets. You can have a business analyst who has certain permissions and he can see a certain view of the data. You could have a data scientist who has other permissions and they might be able to see the entire content of a credit card number. But these are not physical copies of the data, they are virtual. What happens is the original data here at the bottom has rights for the DBA. The DBA can build a view, and on top of that, Cindy might build a further view that could be accessed via queries that Frank writes. By controlling who owns which things and who is allowed to read those things and what the owner is allowed to query, we can provide controlled security that is rooted in the file system semantics rather than in our attempt to write a pattern of which queries will be allowed to succeed or not. File system permissions are, of course, much simpler for people to understand and manipulate, especially if they come from a security or a computer programmer sort of environment as opposed to a database administrator point of view. So, if we think back now, this has been a lot of slides that have kind of slid by, but we have logical views that provide security. It's highly granular because you have all of the power of SQL to define what person can see or not see. It's completely decentralized. There's no single metadata resource that has to be up, that has to be performant, that you have to reload the cache of. And the security allows self-service while still maintaining tight governance. Now, as I said, Drill's goal is to go fast with little information and do even better with lots of information. So here's a little bit about how it actually works. We get fully pipelined execution. And so what we've got here is an execution plan, and you can actually see here this dotted line expresses where parallelism is marked in this logical plan. The initial step of Drill is to convert SQL into a so-called logical plan, which has logical operators here. Starts at the bottom with a scan, and then there's a producer-consumer and a union exchange. There is no parallelism expressed here, and there's only as many types as we understand know exist at this point. But what then happens is that's translated into a physical plan and then an execution plan. And at this point, we begin to see fragments that are executed across the cluster. And part of it that's not executed across the cluster. And we get data flow from the parallel bits into the non-parallel bits. This process of converting from a logical plan to a physical plan and then to actual physical code occurs using the calcite query optimizer, but it also uses special rules that are part of Drill itself, which understand the parallel execution environment. Drill then can generate code on the fly. Data streams in from the bottom of that flow. Data streams in what are called row batches, and they're stored in a columnar format in memory. Each row batch comes with what's called the empirical schema. This is the schema of data types as observed in this data that we have this batch for. If that schema is the same as the previous schema, drill just executes the query. But if it's different, drill will re-optimize in this fragment, regenerate the code, and compile it so that we get full operational speed. And you can imagine this has applicability if we have old data that has column 1, and at some point we decided to convert to column 2 with a different data type. Now, new data will have column 2. So most of the data will have either column 1 or column 2. And we'll probably have a view which will say, if column 1 exists, then we give you this synthesized view. If column 2 exists, we just give you that value. On the first half of the data, the optimizer will throw away the case statement, turn it into straight line code, and always just give us column 1, because the empirical schema says column 2 is always null. So we could obviously do that. In the second half of the data, the optimizer will throw away the fork of the case that talks about column 1. And again, we get full speed. We have no conditionals in the data processing itself. And furthermore, all of the object creations and all of the object references compile away as well. So what's left is direct pointer access to an array of primitive objects, even though we have a dynamic language, which was not type-specific when we originally wrote the code. It's only when it's presented with a block of data that it finally compiles down to primitive code. And at that point, all the types are known, all the types are stored in contiguous arrays so that we get full speed of the machine running on a very tight loop or even in a vectorized loop so that we get these incredibly high speeds even in a dynamic situation. This optimization extends into the RPC layer, which is optimized for that same vectorized sort of transfer. We have optimized readers for formats like Parquet, where drill can do pushdowns into the data reader, and it's a fully pipelined reader that runs much faster than the normal Parquet readers that are part of the Parquet distribution itself. Drill has specific readers for its own needs that increase and accelerate that. The value vector is the way that drill stores data internally. This is an in-memory columnar representation that allows full vectorization of operations because it's a pure array of primitive types that are packed into congenial units. That allows random access to any materialized view without any copying. It allows us to fully memory shred all operations so that we get very, very high access speeds. It also allows us to do interesting things. All operators in drill are expressed as UDFs, the same that you might write. What happens is you compile that, the annotations that you put on your code are used to lift the source code out and put it into a generated set of code so that your code sits directly in the data path and it's encapsulated safely because you can only see the references that you have declared, but the optimizer can now see across all of the code that's generated in the data path. And so the objects that you think you're accessing get optimized away and turn into pure data pointer accesses. This is a unique property of drill, and it allows drill to run at full memory bandwidth speeds on things that look like dynamic code. This runtime compilation is part of the planning process of drill, which delays decisions as late as necessary to get that dynamic typing information fully resolved. This is another unusual characteristic of this, the ability to preserve uncertainty as long as necessary so we never generate conditional code where it's conditional on type, and that wouldn't necessarily be true. So the way that this actually happens is your UDFs get transformed into synthetic code where we inline your code into the main query code. The code model is a generated template into which your code is inserted based on the query itself. Janino is used to compile this on the fly. Janino is an on-the-fly in-memory compiler for Java. And we also have bytecode templates. We do bytecode engineering so that we can directly insert the compiled code without recompiling the entire template. That accelerates this on-the-fly compiling. And we generate custom bytecodes as necessary to adjust the data accesses. That then is optimized by after loading by the standard Java JIT. The optimizations that we do in these things are done both at query time, at dynamic code generation time, and then at execution time. We have special machine code compilation optimizations that are injected into the JIT so that we get very, very high performance. This removes, for instance, all bounds checking from safe accesses, even though your code didn't even know it was referencing vectors. It's still able to remove those bounds checks and drive into machine native pointers. The vectorization does the equivalent of running more than one row of operations at the same time by the use of vectorized instructions. Again, you don't have to annotate that in your UDF at all. The SIMD is brought in as possible and accelerates your code. You also get advanced telemetry out of this because the entire process is instrumented, and you get profiles that are written in JSON. And of course, you can use drill to analyze those profiles. And here's the sort of thing you get out of that. First of all, you get a full DAG, which this is in the web interface for drill, which expresses all of the parallel chunks. You get a different color for what's each called a fragment. A fragment is a bit of code that's generated as one unit and executed in one thread of control. Here, a query has been colored up. And then on the right, what you get is what's called a swim lane visualization. So this light blue section here, you can see, is executed in multiple threads, roughly a dozen threads of control across the cluster. And it precedes, for the most part, but not entirely, the light red, which is the hash join here. We have in parallel dark red, which is a scan and project and filter section, which drives ultimately into the dark green. The dark green is able to start execution as data becomes available from the light red and the dark red, but it can only complete after all of its data is presented to it. The last step of projection and hash aggregation, the result of a group by, occurs here in the light green, and the final output step, which doesn't show here, is right there. So you can see in very, very fine detail what's happening when you run a drill query. You can tell exactly which parts are parallelizing well and which parts are not. The in-memory representation is designed to be efficient, but also efficiently accessible. All vectors are stored as arrays of uniform primitives, and therefore can be accessed in a fully vectorized way. We get column-aware data structures. You don't see them when you write a UDF, but that's what's actually being executed against. And you get some support. Support is ongoing. Implementation is ongoing for fully compressed in-memory columnar representation. We've tested, this is a little bit of an old slide that talks about testing up to 150 nodes. The GA is out, and we've tested in our labs up to roughly 1,000 nodes. And again, no scaling issues have been found at that scale. So this, in a very accelerated 34 minutes, is an outline of what drill is useful for and how it works. It's probably a bit much, unless I'd like to hire you. It's probably a bit much to digest in that 34 minutes, but I think you can see already just little sparks, hopefully sparks that will lead to fires, sparks that say data that you have now could be analyzed conveniently here, either on the small scale, kind of as a grep and awk replacement, or on the large scale as a data warehouse alternative. data which as it is, rather than after an ETL process, can be processed. I was talking about Niels just the other night, how we'd like to be able to put his log parser in that actually drives real logs directly into there. There's no reason necessarily to do ETL out of these data as long as you have a scanner. And the scanner can do arbitrary levels of pushdown. All of the data sources in Drill can expose optimizer rules so that you can pull down anything you like. I just heard a guy in Sweden has put together a JDBC sub-query unit so that it accepts arbitrary pushdown into the JDBC data source. So Drill is flexible enough to do that. So you have a data source which is in fact an entire different query engine that can look at certain tables and understand how to process those. Somebody, I don't even know where they are, produced a Mongo query engine that does the same sort of thing. Took them about 2 weeks. It's not hard. There's some foreign concepts here, but it's not hard to get started doing some very, very cool things in Drill. And I'd very much like to talk to anybody who'd like to do that. My name's Ted Dunning. I work for MapR. We're doing a lot with Drill. Our customers are beginning to put it into production. But I'd love to hear how you guys might use it, any questions that you might have about it.